Okay, so let me just say in advance that this talk is very much it's on the same topic I gave my 15 minutes talk a few months ago, and I want to give more details. So sorry if anyone came expecting to hear something completely new. And also, everything I'll mention today is a joint work with Ori Pazanchevsky. Okay, so the main idea and motivation behind our recent work is very beautiful very beautiful constructions from the 80s by Lubotsky, Phillips, and Sarnak. One pertained to very special graphs we already mentioned today, Ramanujan graphs. The other pertains to excellent topological generating set for compactly group. So I'll begin by reviewing both the results and what we wanted to do is to generalize their results to higher dimension. And unfortunately or fortunately, things did not go as easy as we wish them to be. Okay. So I begin with the more famous of the two results, of the one pertaining to Ramanujan graphs. So the setting is as follows. So X is any graph. The only thing I require on it is that every vertex has only finitely many neighbors. X tilde is its universal cover. The infinite tree, the topological space which covered our graph. Tx is the adjacency operator of our graph. And not the best notation, as you should see later on. Spec X will be the spectrum of the adjacency operator Tx. And
what is the adjacency? The sum of the neighbors?
What is universal cover?
No.
Oh, the adjacency operator. No average. Yeah, it's the actual sum. Yeah.
The actual sum?
The actual sum. Yeah. No average. Oh, please, if anything I said is non-clear, or the abbreviation or anything, please ask away. Okay, so spec X, it's the eigenvalues of this self-adjoint operator, the self-adjoint matrix, and spec 0 of X is spec X after I remove from it at most 2 points, which I'll call them the trivial eigenvalues. Okay, so what are the trivial eigenvalues? So here's a quick recap of Perron-Frobenius theory. So this is an adjacency operator, but furthermore, all its elements in its matrix are non-negative. And the theory of Perron-Frobenius promised me that there is some very special eigenvalue of maximal size. And to it, I can associate some eigenvector which also has non-negative coefficients. So this eigenvalue, this special eigenvalue, as well as its inverse, I deem them trivial eigenvalue. I know them. I dismiss them, and I'm only care about spec 0 of X. And now I can define a general definition of the notion of Ramanujan. So X is Ramanujan if its non-trivial spectrum is contained in the spectrum of its universal cover. So one can really think about the universal cover as the optimal, and a finite object is called a Ramanujan if it is as good as it's.
L2 of the universal cover, right?
Sorry?
You have to put a Hilbert space structure on the universal cover L2.
Right, yeah, sorry.
Okay.
So this is the adjacency operator on L2 of x. And this could be also Tx tilde, the adjacency operator of L2 of x tilde. Yeah. And just to take combinatorics in the audience, which I don't know if there are any, the definition of Ramanujan graphs is usually more compactly described for k-regular graphs. And for those graphs, x is Ramanujan. If the spectrum of x is either plus or minus k. So for k-regular graphs, k is the Perron-Frobenius eigenvalue. So these are the trivial eigenvalues. Or it is contained in the segment minus 2 square root of k minus 1 till 2 square root of k minus 1. And this segment, this continuous segment by a result of Kesten, is the spectrum of the adjacency operator of the infinite k-regular tree, which is precisely the universal cover of a k-regular graph. So this much more explicit definition is just a special case of this general definition, works for any graph. And perhaps a word about the motivation for this definition. Which comes from a result of Alon and Bopana and generalization of it, saying that if you have a family of graphs, all of whom have the same universal cover, and the girth of the graph grows to infinity, then essentially you cannot do better than the Ramanujan property for that family. And what I mean by that is if you take all the spectrums of these graphs and take the closure of it, then the spectrum of the universal cover is contained in it. So asymptotically, being Ramanujan is best you can hope for from a spectral point of view.
There is, I think, an analog of the result I mentioned. There is a weak convergence of measurements.
Yeah. There are quite a lot of results, I think. Unfortunately, I don't remember the name, so I won't say them. But yeah.
Benjamini-Schramm?
It's also related to Benjamini-Schramm convergence and the result of Abert and yeah.
Into non-irregular case, how do you get two eigenvalues? You also put a sign because it's bipartite.
Yeah. Yeah, this is the only reason I put plus and minus, which actually give me a good segue to.
So the minute the algebraist came, he couldn't work out the blackboards.
Yeah.
Usually it's analytic kind of approximates, but
It was wet in the beginning, so yeah. Okay, so the next thing I want to tell you about is what was the breakthrough at the late 80s by the person who just talked together with Lubotsky and Phillips, which actually, okay, so the results I'm about to tell you is solely of Lubotsky, Phillips, and Sarnak. Along with this result, Margulis also gave a construction. But what I'm now about to describe to you has a very special feature. It is explicit, which is very important for this talk. OK, so pick your favorite prime, which is congruent to 1 mod 4. and define the following set of matrices. You see in a minute that this is a strong connection to Sardari talk about sum of squares. Okay, so these are 2 by 2 matrices whose coefficients are the Gaussian integers, and I impose several conditions. So let's take x1 to be positive. I want it, like x1, to be odd and all the other parameters to be even. And I want their sum of square to be equal to prime p. And now I can look at the Cayley graph with respect to the group of 2 by 2 invertible matrices over the finite, the projective 2 by 2 invertible matrices over the finite field FQ, and with respect to the generating set of SP modulo Q. This, in fact, is a generating set of PGL2 FQ, but it's actually more than that. So this is a Q. I'll take it to be also congruent to 1 mod 4 prime. Any, and different than P. Any other prime which is congruent to 1 mod 4. But actually it could be much more general, but this the statement of the result is for 1 prime. And in this specific case, this is a Cayley Ramanujan graph. A few details about this graph. It's p plus 1 regular. Think of p to be small and fixed, while q is growing larger and larger, approximately q to the third vertices. And the example you see in the first lecture of Nasser is where p is equal to 5. So this is a very nice and elegant construction, very elegant construction. And what we wanted to do is just to generalize it to a higher dimensional object. So instead of graphs, we are interested in complexes.
How many generators are there here?
It's a good question. I mean, you don't really need to work that hard to see that this is a finite set, but the exact size of the set, it's not clear, and it will turn up to be a result of a very nice theorem of Jacobi called Jacobi 4-square theorem, saying that without this condition, there are 8 times p plus 1 such quadruples of x1 to x4 which satisfy this condition. With this results just to eradicate simple multiplicities like plus minus 1. And they're p plus 1. And so this is a set of size p plus 1, and this is precisely the reason this is p plus 1 regular. I don't have an easy proof of this result. OK. So next we want to generalize to higher dimension. OK, so I'll restrict to a very, still a family of objects of higher dimension, but more accessible. So I'll only consider universal cover. So X will now be any simplicial complex, but I'll only restrict those who have universal cover, which is the Bruatitz building. of any type you choose, which are, this is simplicial complex analog of symmetric spaces. And the first problem I'm facing trying to generalize it to higher dimension is what kind of adjacency operator do I pick? So for graphs, there is one very natural, but even in two-dimensional, there is more than one. You can think of adjacency operator on the vertices, on the edges. Even for the vertices, there are two different very natural adjacency operators. So I'll take all of those. So I'll take all Ivahori Heke operator. Well,
when you say vertex building, it's vertex building for some group.
Yeah. And so, okay, so I take the Ivahori Heke operator, and
on which space L2 of G modulo Ivahori?
so it's also a good question. So the beginning of the theory, people only consider the vertices of the Brotitz. So I forget about the Ivahori. But now we understand that the adjacency operator on the edges are just as, if not more important than the vertices. OK. So I'm taking all of them. Where is my definition of? OK, so I have the adjacency operator. This is why I said that spec x is a bad notation, because now I'll take, if I'm forgetting about the Ivahori operators, then the Heke operators commute, and then I can take the simultaneous spectrum, and then I can define. I also need to define what are the trivial eigenvalues. I won't do it, but I'll tell you that some complex is Ramanujan if the spectrum of the operators on X is contained in the spectrum on the universal cover. This is one way to extend this definition.
I'm still confused in the commutative commuting case. It's not all vertices, but one class of vertices.
And no. OK, so I fell in the same trap I tried to avoid. OK, so thank you for raising this point. In the case of only taking the adjacency operator on vertices, but there are different coloring of the vertices, so I take this is of color 1, color 2, and so on. Then I need to take the simultaneous spectrum. So eigenvalues or eigenvalues to all T. OK, so thank you very much. So I'm taking the simultaneous spectrum. This was the original definition. Now, once I add all the other interesting operators, I can just pick one. I'm sorry, I don't need it to be the simultaneous to all of them. I need that it will be right for every individual one. Thank you. OK, so this is now the definition for higher dimensional Ramanujan complexes. And indeed, there were, in the past, 15 years and more, there are several constructions. I'll mention a few names: Lubotsky, Samuels, and Vishna, Lee, Salviniazzi. Several construction of Ramanujan complexes, all of them coming from A tilde type building. But I do want to emphasize that none of them follow the fact that they are over the integers or Gaussian integers or anything of characteristic 0. All of the constructions are over positive characteristic rings of integers. And the reason this is important is because of the next result I'm about to mention, which is the second interesting result of Lubotsky, Salmons, and Lubotsky, Phillips, and Sarnak from the 80s, which in recent years found connections and application for quantum computation. So let me begin by setting up the setting. So I'm switching to a completely different subject, a priori, completely different subject. So G infinity will be a compact.
By the way, I saw today that IBM is selling quantum computers without using our gates, so I'm not happy. I don't think their computer works. I think it's a classical computer sold as it. I'm serious. They don't.
Really?
You can buy one. You can order it on Amazon.
What do they claim to do?
I think they have 20 bits, but I think it secretly is running on a classical computer with one little tweak which was quantum. So I don't think it's doing anything that.
So
They say it doesn't do anything that's new.
so
It's just you'll be.
factor 6 into pi?
Yeah, something like that. You'll be the first owner of a quantum computer.
Okay. Okay, so the setting is we have some compact Lie group, and we have to it we have some Haar probability measure and a bi-invariant metric, and I'll denote by bx of epsilon. X is some element of our group. Epsilon is, of course, a non-negative real number. And I'll denote by it a ball with respect to the bi-invariant metric. This is the ball around X of volume epsilon. So I parameterize my ball with the volume instead of the radius. Once you have one, you can immediately find the other. This is I parameterize it with the volume because the definition would be more natural in this setting. And if you have a set of points, then I'll denote by bx. X is a set epsilon to be the union of the balls. Volume epsilon around each of the points in the set. And for any finite set S in my group, denote by SL the words of length L in the alphabet S. Okay. So the first definition.
Do we assume S symmetric or
No. No. And it's quite general. And the first definition I want to give is it doesn't have anything to do with quantum computation. Say that S is an optimal generating set of the compact Lie group G infinity if, okay, so even before I'm saying optimal, what do I mean by generating set? Of course, I'm not meaning that a generating set in the abstract sense, because S is finite and G infinity is smooth. So I'm talking about topological generators. That is, every element of G infinity, I can approximate it with words in my set S, get close to it as much as I want to. And the optimal is now trying to make that idea more quantitative. Okay, so let me start to motivate the definition by writing something wrong. Okay, so what I want to say is that I'm taking all the balls of the radius 1 over the size of the set on the words of length L, and I want to make sure that the complement of this union of balls is very, very small, approaching 0. So obviously, this I cannot take the radius smaller than this. A simple union bound tell me that. And this would be amazing if I can pick such a set. I don't know how to pick such a set. This is too good to be true.
It's probably not true, right?
Sorry?
Probably not true.
But yeah, it's definitely. I mean, even for spheres, I have no idea how to make such a thing. Okay, let's take intuition from a random set. So if this was a completely random set, then a coupon collector argument tells me that I need to add some log factor. So this is random, and random, as we all know, is good. And what I'm allowing to myself a little wiggle room, because I don't know how to even prove only the log. So I'm allowing to myself some power of log. That's it. I think square might suffice, maybe. Okay, so but to make whatever I'm saying afterwards true, let's write a polylog. And this is very close to the best that we can hope for by random methods. So this is, at the head here, an almost optimal generating set. And to relate it to the previous two talks, or to the first talk of Nasser, this is it's an almost optimal. This is almost covering of the entire group. This is the K bar and not the K. So it's an almost optimal, almost generating. But this is a definition, and it's not easy to find such a generating set. And as I said before, the second very beautiful result of Lubotsky, Phillips, and Sarnak from the 80s states that for the group of 2 by 2 real unitary matrices, for every prime congruent to 1 mod 4 that you wish, you can take 5, for instance, then the same matrices, set of matrices from before the same condition from before is an optimal generating set. And okay, so this is from the 80s, and in recent years, actually, such optimal generating set with an additional property were found to be useful for quantum computation. Okay, so now I give the definition of a stronger notion. The same setting from before, but now S is called a golden gate set of G infinity if, so first of all, this is a strengthening. So S is an optimal generating set. And the second condition is that there exists some polynomial algorithm such that given an element in the compact Lie group, some epsilon bigger than 0, some positive integer L, it returns an element epsilon close to x, which is a word of length L in my set S, if such an element exists. Otherwise, it says null.
It says nothing, or it doesn't terminate.
I wanted to terminate, to tell me. But
No.
so obviously I don't need to, obviously it's more interesting in the case where there is such an element. I'm not trying to make life.
I don't understand what B says again.
What's
What the
B?
big B is,
Yeah, so there is some polynomial algorithm.
Oh, algorithm.
Yeah,
Polynomial in what?
polynomial in the input x, epsilon, and L in the size of the input, like log of epsilon, a log of 1 over epsilon, log of L, and log of to write some number, I need like poly 1 over epsilon. So I need
Information content of the
yeah. Yeah. So maybe it would be best if epsilon was just a rational number, and I need to have it in polynomial in the denominator and the numerator.
Logarithm.
The log. Sorry. Yeah. Sorry. Okay. So unfortunately, this is okay. So let me say that a year ago, very recently, Peter Sarnak with Ori Parzanchevsky published a work actually introducing us to the notion of golden gate. Well, it was introduced in the letters of Peter, but it was one of we first came informed with such a problem of polynomial algorithm of this type. And in that paper, they proved two results. There are good news and bad news. So the bad news first is that problem B, as stated, at least when I'm looking at the set, this beautiful generating set of LPS, is an NP-complete problem. Is NP-complete. This is the same thing that Nasser mentioned in his talk. Also, there is some randomized reduction. I'm assuming factoring of integers, but the to note is that this is too strong, too much to hope for. Exactly. So allow me to adjust the definition just a little bit.
By the way, Don Knuth thinks P equals NP, so it's not necessarily by everybody's account too much to ask for, but he's unique.
Okay, so for those of us who don't believe that P equals NP, allow me to weaken the definition just a tiny bit. So I'm introducing here some number which depends only on the big group, G infinity. My guess is, I mean, you can, I'm pretty sure that you can take it to be smaller than the dimension, or smaller or equal. And what I'm requiring is that instead of give me back the shortest word, you give me back n times the shortest word. And for this problem, let's call this B prime. So problem B prime for the LPS set is a golden gate set.
Is there a conjectured threshold? You have a factor times there. So if your factor is big enough, you can do it in polynomial time. Then if you can't, of course, there must be a range in which, there must be a transition in which it goes from one to the other, right?
I can.
Firstly, you should mention Ross Selinger.
Yeah.
That's
My
my
question,
question.
I think the shortest is NP complete, and if you jiggle it a tiny bit,
You think
it's not one of these, what they call PCP theorems.
there could be some range.
Yeah,
there
yeah,
where
I
it's
don't know, I just
Yeah.
don't know. Okay, we don't. Yeah.
I don't understand the original V. You did not ask in the original V that you had the furthest one.
Well, I actually did, because I'll pick L to be the shortest possible that is guaranteed to that such an epsilon exists by the optimal generating set definition. And then I'm asking you to bring it to me.
You
And
can change the sets, you see, you can change
Yeah.
epsilon by doing epsilon's 1/2 to the L and then ask, is there one or isn't there one? And then the next, so you can actually build in the shortest in that kind of formulation. It's not equal.
yeah, so it's I can so if such an algorithm exists in the original B, then essentially you can bring me the shortest one by this requirement, because there exists such an element. You have to bring it to me. There have to be a polynomial algorithm, and this violates what Parzanchevsky and Sarnak, or maybe it's proved that P equal NP. So it will be a nice proof.
I should, there's something here that, if I may interrupt here, there's something that I learned from this that I wasn't aware of, which if I was aware of 20 years ago, I would have always been telling everybody. So let me share it with you. Some people think factoring is hard. I don't. Okay, I think that's very easy to factor. I can't. But suppose I ask you, I give you a number n, and I ask you not to just find is x, what is there, give me x, y equals n, non-trivial factorization, but I give you three numbers, n, alpha, and beta, and I ask you, that's my input, and I say, is there x, y equal to n, I'm giving you n, alpha, and beta, and x is between alpha and beta. That's NP complete. So you ask this little extra approximation part to this, and I can show you guys afterwards. And that's sort of the source of this whole thing. So the minute a quadratic equation may be solvable quickly, but a quadratic equation with an approximation, which is what's deeply embedded in there, even just in one variable, is already NP complete. So it's kind of frightening. So I've always felt that factoring is easier than I thought.
So this comes from subset sums?
Yes. Comes from subset sums, absolutely. But it's kind of shocking, isn't it? It's like I say, factoring is easy, and then somebody says, yeah, well, all right, factor, put x between alpha and beta. That's already very difficult. I think that was first observed by Noga Alon and somebody, I forget the other name.
I have your paper here, so I can.
Now, Sudan popularized.
Okay, so
Could you tell again what the final form of B is?
so the final form of B is that there exists some number depending only on the group.
Killian and Alon.
So there exists some big N depending on the compact Lie group, and there exists some polynomial algorithm. Oh, yeah, I know. If such exists in, yeah. Yeah. So there exists some polynomial algorithm such that giving x, epsilon, and L, if there exists an element, a word of length L of epsilon proximity to x, then you can find me with the algorithm an element epsilon close to x of word n times L.
Exactly n times L or at most n times
I don't think it will matter if I just require at most n times L, but I think that the longer the words you're allowing to me, I can, they don't push me away. I can get even, it's like a, yeah. I mean, because of this condition, you can see that n times L will be even closer to 0. Yeah. But if it's confusing, at least to me, then smaller or equal to n times L, it's fine. Okay, so I don't have a lot of time, so I want to tell you about what is the scheme of constructing such both graphs, scalar Ramanujan graphs, and Golden Gate set of the works of Lubotsky, Phillips, and Sarnak, and they use the same scheme, and it has to do with p-arithmetic subgroup. P-arithmetic groups. So what you need is to find an algebraic group over Q. Let's assume that I have some model such it's over the integers, such that when I put inside the real numbers, I get my compact Lie group. And when I put inside the periodic numbers, I get a non-compact compact group. P is some fixed prime. And an important example to keep in mind, R is some ring, and the example is the group PGUN, the projective, similitude, unitary, n by n matrices, which is by definition, its elements are matrices in the ring, n by n matrices in the ring R after I joint square root of -1, and I impose. So this is a conjugate transpose with respect to the automorphism keeping R fixed, and square root of -1 send it to minus square root of -1. And I want that conjugate transpose of G times G to be a scalar matrix. And then to make it projective, I divide by the center. Next, I want to have some p-arithmetic subgroup. So what is a p-arithmetic subgroup? It is a finite index subgroup of G z over 1 over p. And this is the principal p-arithmetic subgroup. This is a finite index. If
dividing by the center is not exactly what you need to.
Yes, for this example, it works. Yeah. Yeah. The magic of the Gaussian extension. Okay. So this is a group which sits naturally both in G infinity and GP. But it's actually useful to think of it as it sits diagonally in their product. And in their product, it is compact and co-compact and a co-compact lattice. So lambda is also a co-compact lattice. And lambda Q will be some congruence subgroup of lambda of level Q. Okay. I'm short on time, so let me just I'll tell you what I need. In order to get the Golden Gate set and the Ramanujan graphs, what I'm looking for are a pair of lambda and lambda Q. Let's call them a golden pair. If two properties hold. So the first property is the Ramanujan property. Okay, so there is a, it's slightly technical to see at first, but it says that for every pi, which is, it's a representation, but it's irreducible, infinite dimensional, spherical, sub GP representation of L2 lambda Q. Okay. So for my subgroup lambda Q, there is a natural space, taking the quotient of it, looking at L2 function of it. This is a Hilbert space. It comes equipped with an action of GP. And I'm looking at specific factors of this space. And I want them to be good. Where good has a mathematical notion, mathematical names attached to it. It's called tempered. So this is what I want. And I'll say in advance, this has to do with the Ramanujan conjecture, but prior to the counterexamples given by Petesky, Shapiro, and Howe, I'll call this condition the naive Ramanujan conjecture, as opposed to the generalized Ramanujan conjecture, which should hold in general. This shouldn't. And the second condition has nothing to do with lambda Q. It only has to do with the big group lambda. It acts simply transitive on the Bruatitz building of the p-adic group GP.
You mean on the vertex?
On the, yeah. Yes, thank you. On the special vertices. Yeah. Special vertices. Now, this is a very rare property. It usually doesn't hold. And let me show you another more compact, for me it's more natural way to write simply transitive. So I have my big p-adic group. I have my arithmetic subgroup. I also have, to my big p-adic group, there is a compact subgroup. Usually it's a good compact subgroup. And in the special cases where this and this happens, I have a simply transitive action. If you like working with Adele, also there is a nice interpretation. I should say this is strictly stronger than having just class number 1. So if
Will you have only one kind of special vertices?
I'm usually choosing P to be away from the ramified primes of the group, making sure that I don't have a two hyperspecial kind. And usually I'm working with unramified groups, so I have one hyperspecial kind. And
One for some group.
once the orbit, like take all the vertices, like in the case of a PGL,
Yes.
then I consider all the vertices of the same type, and I wanted to act transitive on all vertices. Yeah. So if there are all the vertices, so I really want, yeah,
All special vertices.
yeah, yeah. As much as the thinking allowing me to get. Okay, so why did I state this definition? Is just so I can write the following claim, a very compact case. So one, if lambda lambda, or lambda lambda 1 if you'd like, is a golden pair, then from this I can get a golden gate set for G infinity by picking a very nice generating set of data, which has the action on the Brotitz building. Yeah.
And you can navigate?
Navigation is, it's always, I won't say always, but once you have the transitive action on the Brotitz building, on the special vertices,
Then you can navigate
yeah.
On there, but the approximation problem.
The approximation, it's, for me, approximation is much harder than navigation.
That
Yeah.
wasn't part of the definition.
Yeah. Yeah. I did the problem B to two parts, the navigation and the approximation, but yeah. So I won't get into the details, but which I learned from you. So the navigation, it's the problem of once you have some matrix, once you have some word just to solve the word problem. So I have a word, but it's not written as a word. It's written as just a matrix element. And then I want to write it as a word. And this is, it's easier to do because you really need to just look at the action on the Brotitz building and to reverse the geodesic back to the origin. That's the navigation problem.
So you have to find a geodesic between
Yeah.
triangles.
Yeah, two vertices. But it's quite easy because you just need to check, like put all the neighbors, all the generating set, act on them, and one of them you can see from taking evaluation on all the elements of the matrix, it's smaller, it's closer to the origin. Yeah, and the second claim is that if lambda and lambda q is a golden pair, then you can have an explicit Ramanujan complex. And if GP is PGL n, then it's a Cayley complex. Otherwise, you need to invent something which is not a Cayley complex because Cayley complexes, all the vertices looks the same and quotient of buildings. Yeah. Okay. So let me just quickly put both results of a LPS in one basket. So their algebraic group is PGU2, which is isomorphic to the Hamiltonian-Quaternion modulo the center. And their arithmetic group is very nice very natural choice. Just need to add this simple congruence condition. And they prove that this is a golden pair for any Q. And they use two classical, or actually more than two, but the fact that the Ramanujan property holds is due to a combination of using the linear resolution of the Ramanujan conjecture for PGL2, and then using the Jacquier-Langlands correspondence to move the validity of the Ramanujan property to the inner form PGU2. And the simply transitive property also holds, and as I mentioned before, this follows from Jacobi four-square theorem. So a lot of classical number theory meet up in one theorem. And again, beautiful aesthetic subgroups, and both property holds. And what we want to do is just to generalize this to higher dimension. That's what our goal was, and we didn't generalize to higher dimension. We barely managed to generalize to PGU3 because apparently these two properties do not live well with one another. So there are two ways to continue from here. One is to pick some algebraic group which comes from, so they work with quaternion algebra. It's natural to think, let's take bigger division algebra. Okay, so the Ramanujan property for bigger division algebra could be made true. And this is appealing to the work of Harris and Taylor.
So how do you get the Kaufman group?
It comes from a division algebra, but I need to add to it involution of the second type.
So it's a form of unitary
Again, yeah. But yeah, all the generalization will be forms of unitary, but I'm treating separately division algebras with matrix algebras. And the reason I treat it separately, because for division algebra, the Ramanujan property is, the naive Ramanujan property is aligned with the generalized Ramanujan property, which is great. Unfortunately, the simply transitive property fails, and the reason it fails is the transitive property fails because of the mass formula. So one can see that taking one strengthening of Siegel mass formula and Minkowski's not trace formula, mass formula. I said mass formula at first, yeah. Yeah. So Prasad extend the work of the mass formula to calculate volumes of S arithmetic groups, such as what we've been dealing here. And just looking at its formula and try to plug in groups which come from division algebra, you see that you have no chance of satisfying the property of it acts transitive. Simply, I don't even think about.
So class number grows very fast.
The class number will grow, and so for me, the second it grows above 1, I give up, and I'm trying to think of new things. Yeah, just a few calculations.
It can't be 1 except for finite numerical cases because of the compactness of infinity. It's always the definiteness that makes it.
Yeah, and the fact is that
For a function field that you can do it.
yeah, for function field, there is a miracle that for every dimension you have groups of class number 1. And you have, for every PGUn, for every n as big as you'd like, you can find simply transitive subgroups. And for zero characteristic, this is far from true. And actually, there is a nice work of Muhammadi and Golsafidi trying to find all the simply transitive subgroup over characteristic 0, and you cannot go above PGU8. So, and
Because the quantum guys only want a unit.
yeah, they wanted 2, 4, and 8, I think. Yeah. So it's okay. So, okay. So the next thing is we try to look at groups coming from matrix algebra. Okay. So now the simply transitive. Well, in some cases it's true. Again, not for n bigger than 8, but in some cases it's true. But now the Ramanujan is false. And this is precisely because the naive Ramanujan breaks down basically it breaks down for groups coming from matrix algebras. So we have two bad news, which seems that we should stop. Now, let me just write what we managed to prove, and then you'll stop me and say that I'm lying somewhere. So we're looking at PGU3. And we're considering the following group. With a congruous condition modulo 2 plus 2i. This is some number over 2, over prime 2. And the congruous is a condition only above and below the diagonal. Sorry, only a condition on the diagonal. Above and below, you can pick whatever you want. And the claim is that this is a golden pair for any odd Q. Okay, so this is what we were able to prove. And there are two things that seems almost doesn't seem to make sense. One of them is that the statement before I just claimed that for groups coming from matrix algebras, the Ramanujan property fails, and here I claim that it holds. And the reason it holds is because I impose this condition on the level. And this is only for 3 by 3 unitary matrices. And this is much, we really rely heavily on the book of Rogalski. This is really our Bible for this paper, which described the unitary representation of PGU3, or of U3, actually. And in that book, he really found out which bad representation violates the naive Ramanujan. And he showed us that all of them have interesting level over the prime 2. So this is the trick to get the... And of course, we needed to use the correct, to get the generalized Ramanujan conjecture. Of course, we can't go away from it. We needed an extension of Delin's work by Shin, and a lot of Langland's factoriality. And the fact that it acts simply transitive, we prove it. what's even more basic is the question is that why is this even a group? So it's a calculation. The last time I gave this talk, people came to me after the talk and really confronted me with the fact that groups should act on something. I have no idea where this group acts on. I don't know what is the. I can't give you intuition. The only thing that I can say is that
It's a group.
yeah. Yeah, it's a group, but I should say that this is really a calculation. You don't really need to invent the wheel. We knew that we are looking for something which lives up to level 4. Okay, so it's a final calculation to try to figure out. Yeah, okay. So I think I'll finish. I stop here. Thank you.